Okay, listen, come on. I need a new battery for this thing. Alright, the last day. I know some of you were starting to tear your hair out a bit the last day, but maybe by working through some of these examples it'll make a bit more sense. So we looked the last day at states, and we looked at how Simulink works. And it's quite complicated. I mean, as you know, I've always described MATLAB as a black box, and certainly Simulink is yet another black box in terms of how it works. So we looked at solvers, and you know, you give Simulink a problem and you say to execute the model over a certain time frame, and it decides itself then a whole load of stuff. So in terms of, we looked at the sequence of events, and particularly we looked at how you can select for your model, if you go to the configuration parameters. So if everyone's got a model open, go to configuration parameters, which you'll find under simulation. So if you click on simulation tab and go model configuration parameters. Okay, so as you can see, it brings you up this dialog box here. Everyone got that? And you can see variable step here. If you click on variable step and look over here at the different types of solvers that you can use for variable step solvers. So click on the tab there and you see a whole range of them. So ODE stands for ordinary differential equation. And you can see you can select different approaches. So the last day we just briefly, and we're not going to go any more than briefly, looked at how Simulink gives you different ways to solve a problem, and some of them are more accurate than others. We looked in particular at ODE 45, and what we saw was that what it does is it looks at the fourth order solution, it looks at a fifth order solution, it looks at the difference between those two solutions and says, you know what, there's a certain difference. And then it says, right, we call that an integration error. And then it says, right, if that error is unacceptable, it means the time step we've taken is too large. We need to reduce the time step. So we looked at this. So if you're using a variable step solver, you'll also see these fields, which allows you to set those tolerances. So there are two tolerances. One is the absolute tolerance, which looks at the absolute value of the state value, and it multiplies it by some factor, which by default is 1,000. So it looks at 1,000th of the state, and the absolute tolerance is just a value for that state differential. And Simulink works around those two. So up here where the state is high, it means 1,000th of that value will be fairly high. So that's the region. When the state is high, it's in that region that the relative tolerance controls the step size. If the state is very low, then of course 1,000th of that state will be tiny. And in those intervals, it's the absolute tolerance that dictates the step size. So this is the algorithm here that works in the background. So at each step, Simulink does this, and if it finds that either of those tolerances are acceptable, it goes on. Else it reduces the step size, continues, checks the error until it comes in within the acceptable limits. And eventually you get a value, and the model completes. Okay, so what we finished off the last day was we looked at this very simple model. We have a pulse being generated, we integrate it, we add 3 to the integration, and we get the output. So here's our pulse, here's our integral in blue, and here's the bias added to it, okay? So that's the model you've all opened. So if you look at the configuration parameters, and if you go to fixed step, so select fixed step, and make sure that the fixed step size is set to auto. So in other words, what you're saying is, I want this model to run in fixed step intervals, but I want you to decide what the fixed step size will actually be. And what Simulink does is it looks at the pulse that you've created, and it sees here that the pulse has a period of 1 and a pulse width of 50%. So it chooses a step size of 0.5. Okay, so the way I showed you the last day to look at step size is, where are we? Here. So if you type in here, so when you run that model, it should run okay. And if you go plot the difference in T out, let's see, has my model open there? Isn't that opening? Propose a solution here. What am I doing wrong here? Busy. Should I shut down MATLAB again?
Could just draw.
Hmm?
Could just redraw.
Okay, have you got that working, by the way? Yeah?
Yeah.
Something's happening here. Finally. Okay. Okay, so fixed step size is auto. Need to apply it. If you go to the pulse, you'll see here it's 30%. Wait a second now, I just set it to what we have in the notes, 50%. Okay. Save your model. Alright. So you can see, is that okay, Dave?
Yeah, it's good to plot difference time out.
Okay, so if you go to alright. Okay, so you can see it's a fixed step size of 0.5, yeah? Yeah, okay. This is a different version of MATLAB than the one I have. But anyways, if you needed it, I showed you the last day that I had problems in that it shows the x-axis or the y-axis to be 0.49999 and 0.5000. So they all look, it was a funny old display. So you can actually edit all that if you want to use the edit axis properties. You can set the minimum and the maximum here. So there's your y-axis. It'll eventually come up here. There's your y limits. Yeah. Okay, so you can go 0 to 0.7, we'll say. Okay, so okay, now the next thing is if you right. So then what I've done here, we finished off here the last day, I changed the pulse width to 30% and reran it, and lo and behold the output vector is much larger. It's size 101. Why is that? Because Simulink has to look at the shape of the pulse, and then it has to determine a step size, and it says, right, 0.5 is not appropriate now because the pulse is changing at 0.3, so it sets a step size of 0.1. Because it sets a step size of 0.1, you have many more elements in the time vector. All right, so everyone getting that? Yeah? Okay. And then finally, for your third time running it, just go to variable step solver. So what you're essentially saying to so go to variable step, and again, once you go to variable step, you see these relative tolerance and absolute tolerance. Really, we're not touching those at all. And as I mentioned, that's the list of different solutions you can use. Those all making sense to you, Kevin? Yeah. Would you have covered all those, yeah? Use them? Some of them anyways. Yeah, okay. Alright, so apply that. So now essentially you have a different solver completely. You need to save it and run it. And if we go to the workspace, you will see... Sorry? Doesn't matter, ODE 45 is fine, the first one. Yeah. That's the one we've used for any of that. So you'll see the time vector is now 65 by 1, so we've gone from 101 to 65. And again, if you plot the iterations of that, you'll see something like this. Alright? So as you can see, as the model proceeds, actually Simulink is changing the step size. And again, if you click on the timeout vector, you'll see that for yourself anyways. So the model runs from 0 up to 10, but you can see the step size, 9.4, 9.5 is 0.1, 9.5 to 9.7 is 0.2, etc., etc. Alright? So essentially you're leaving it up to Simulink to decide. But remember, once you're in variable step, it essentially will continue to reduce the step size until the tolerance limits are being met. So if you bring that down to 1 by e to the minus 4, what will happen, do you think? So what you're saying is the acceptable error is now much smaller. So that you'll find the step size will reduce. It depends really on whether it's the relative tolerance or the absolute one that's actually the determining one. But ultimately, in theory, what will happen is it will run more often, therefore it will take longer to run. Your results will be a bit more accurate in that the integration error will be smaller. Don't have a marker here. What we do? So you can imagine this is the actual parameter, and we're taking discrete steps along that. So you can imagine the straight lines somewhat between that. There's a small error here, there's a small error there, there's a small error there underneath the straight line. So again, if you reduce the error margin, what will happen is it will take smaller and smaller steps until the errors are much smaller. It takes longer to run, but gives you a more accurate solution. So it's a trade-off, essentially. Okay. Right. So, the other thing I mentioned is when you look at the variable step solvers. So variable step solvers are really good in the sense of not only do they allow you to control the error, it also means that Simulink will pay particular attention when it sees things changing. So in other words, here we have a sudden change in a parameter, so if we were to explode it, it looks like that. Alright? Now if you have a fixed step solver, there's a danger that essentially you would take a sample here and a sample there, which means essentially your iteration will go here and then across to there and down again. So you have a large error. So if you're using a variable step solver, Simulink will detect this discontinuity and say, need to pay particular attention to here. So it will run lots of iterations, lots of time steps, so you'll get a much more accurate solution. Okay? So that's called zero crossing detection. And you can see it here, zero crossing control. So by default, it says enable all. So what I want you to do now is open up that ZC detection. So that open up the other model that I have there. Okay, and just run it as it exists. I'll do that as well. Give me a week. No, we're okay this time. Alright, so if I go to configuration parameters, you'll see here the start time is 0, the stop time is 15. Set it here. Actually, first of all, go to enable all. So in other words, you are setting zero crossing control. So essentially, as Simulink is running, it will check for every discontinuity. We're not going to go into these details. In fact, I haven't looked at this version of Simulink. I'll have to look at those. But once you set those, apply that and run the model. So again, if you go to configuration parameters, just make sure zero crossing control is set to enable all. Alright? So what you're saying to Simulink is keep an eye out for every single instance of anything unusual in terms of a sudden change in direction. And then run the model. And have a look at the scope. Alright? So it's an interesting piece of, it's an interesting model that does nothing really except show you stuff, but in terms of the real world, I'm not sure where you'd use it. So as you can see here, you have a sine wave, and of course that sine wave just goes straight through via a multiplexer. So you can see the sine wave, which in front of you is in yellow, right? And it has an amplitude of 5, so it's kind of hard to see here, but you can see it in front of you. So that is the underlying sine wave, all right? Here we have a switch block, and if you double click on the switch block, alright, you'll see that its threshold is 5, right? Now we've looked at a switch block a couple of weeks ago, and as you know, a switch block has a threshold of 5, which means if the value is greater than or equal to 5, it uses, which input is it again? This one, yeah, okay. So if you look at, essentially what you're doing is you're switching here based on the clock time. So this is the simulation time. So you can pull that over from the library browser. So essentially what you're saying is you switch between the inputs, between this one and this one, based on the clock time. The clock time threshold is set to 5. So as you can see in your model here, that what are we seeing in the output of the switch? Well, that's showing in purple. Okay? So here we have the simulation time on the x-axis, and when the simulation time reaches 5, you'll see something funny happens. You get this straight line down. So what you're doing is you're switching between one output and the other. Now we're going through an absolute block here, and remember, an absolute block just inverts the negative. So if this is a sine wave, and you put it through an absolute block, what you get is essentially this here. Alright? Okay? So what we're doing is we're getting the sine wave put through an absolute block up until 5. So you get this up here again. Now at 5, it switches to the top. Right? It switches to the top, but we have a saturation block here. Right? Which means that the maximum output of this is 2. So essentially it now comes down here and it maxes out at 2. Alright? So the only purpose of this piece of Simulink code is to generate lots of sudden changes. So you can see here that the actual output here is quite tight on the corners. Alright? So what I want you to do now is go to the block parameters. So here, model configuration parameters, and disable zero crossing detection, which means it will not look at all for any discontinuities in your model. Make sure you save it. And rerun the model. Okay, so as you can see there, that we're now getting these rough edges essentially to the output. Why? Because Simulink is no longer checking for those. So again, it's all about accuracy and speed. So I mentioned in speed. So in the latter example there, what you're saying is, and if you were to use TikTok to measure the simulation runtime of that model, what you'd find is that the model runs much faster when you disable zero crossing detection. But of course, the downside of that is you get a much less accurate model, because obviously you're getting these strange incidences here where the model is essentially not detecting correctly what's happening precisely at these points here. Okay, anyone got any questions? All right, let's open up. There's another model on Blackboard. Let's look at that one. got Blackboard? Who's got Blackboard open here? Show me. Yeah, let's open up the wind turbine model.
Yeah.
You'll also need the script that runs with it. Yeah. So essentially every exam paper has, and I'll say it for this year's class as well, has a question on it that will either be a wind turbine or a tidal turbine. Alright? And they're both really much the same, as you know. So that is, I mean, essentially, as I said to you at the start of the year, if you've done the labs, the exam is really easy, because ultimately what you're asked in the exam are variations on what you'll have done in labs. So what we have here is we have a script that essentially recreates the power curve for the wind turbine. So if you go to the polynomial block on your wind turbine, you'll see the coefficients that define the curve, and that curve essentially maps wind speeds to megawatts. Alright? So the script is here. So in every exam you'll be given a power curve, and you've got to read off the power curve from the exam paper with your ruler. It doesn't have to be too accurate, because obviously I won't be running them, don't worry. But you can see here, you're taking the readings for wind speed, so 0 meters per second, 1 meter per second, 2, 3, 4, right up to the max, and then you're generating the coefficients using the polyfit function. Alright? So remember, there's two ways of doing it. One is the easy way using polyfit, the other is the hard way from first principles using the matrix division that we covered. You'll be asked one or the other. And it'll be very clear. So if you're told to use polyfit, don't be wasting your time using matrix division, because it'll just take you a few minutes and you don't get any extra marks for it. Alright? So ultimately all this piece of code does is it generates those coefficients. And finally what it does is it reads in from an Excel spreadsheet the actual wind speeds. So remember, it serves two purposes. One is to generate the coefficients for the power curve, and the second is to read in the wind data that you're going to use for your model. So the model runs over a period of time, and you're setting the time using the vector t, and the speed data, you're taking those from the Excel spreadsheet. So then if you go to the model here, and again you go to model configuration parameters. This is the bit that we were talking about yesterday that I was a bit surprised none of you seem to remember this. We did cover this. And you go to data import and export. You have to specify that when you're running the model, where does the model get its data from? Well, the script defines the vector t, and it defines the vector speed, but you have to list them here in your configuration parameters. Alright? So in other words, when you run the model, the model will look for a variable called t, which Simulink knows to be time. I mean, you could call it bananas for all Simulink cares. All it looks for is the first variable there. It says that's the time, which is the independent variable, and speed is the dependent variable, which you create in your script. Right? So here we have t for time and speed for the actual speed, meters per second, read in from the Excel spreadsheet. So if I run that script, it will generate the data. Oh, sorry, I don't have the Excel spreadsheet with me. Yeah, so it'll give me an error. It won't give me an error. So essentially, as you can see, oh, sorry, I have the data actually there on the memory stick. Okay, so as you can see, it populates the everything I need. T is the time vector here, and speed is the wind speed. So essentially, we are now ready to roll. Because remember, all the model needs is the coefficients, p coefficient 5, and it needs to read in the speed data. After that, it has everything it needs. So that model should now, hopefully, run. All right. So remember, that was a very unwindy month. Unlike this year, 2010 in December was essentially freezing cold with no wind. So as I showed you in the lectures, very little power output. All right.